Hello and welcome to the chapter 15.5 lecture on directional derivatives and gradient. So, given a function f of xy, the directional derivative in a direction u, where u is a unit vector, which is kind of a pure direction at a given point, is informally the slope of the surface in that direction. So if you're standing at this point a comma b, then the directional derivative in this direction u would be the slope in that direction. So it's very much like partial derivatives. In fact, del x is the directional derivative in the positive x direction, and del y is the directional derivative in the positive y direction. And formally, the directional derivative is defined as such. It's denoted with d sub u, where u is the unit vector in the desired direction of f of ab. And the way to read this is that, well, it's like the calculus 1 definition of a derivative, and we need to make sure that u is a unit vector, because that way, as we go hu1 and hu2 in the x and y directions, then their sum, hu, is such that the magnitude of hu is the magnitude of h, which is just h is already positive, times the magnitude of u. But the magnitude of u is 1. This is why it's very important that it's a unit vector. So it's just h. So in other words, u being a unit vector makes it so that we actually do move just an amount h in the desired direction, and therefore it's the rise, the change in slope, as we move h in the desired direction over the run, which is h. Okay, and we can apply this definition directly to find a partial derivative, and it's very much like what you did in calculus 1 before you learned any derivative rules whatsoever. You would take a function, plug it in to the formula for the derivative, and compute that limit. It's kind of tedious though, and there isn't much point in doing it. So let's skip straight to how to compute it in a slick way. So consider a function f of xy and a unit direction u with components u1 and u2. Then what we can do, we're going to derive the formula. What we can do is parameterize x of t is a plus u1t and y of t is b plus u1t. And what each of these do, this means that we are moving in the direction, well, u1, u2, from our desired or starting point, ab. Okay, and then we do this clever thing. That would mean that the directional derivative in our desired direction is d dt of f of a plus u1t, comma y, which is now b plus u2t. And then we can apply the chain rule, which we learned the previous section. Plugging into the chain rule is del f del x del t plus del f del y dy dt. But by definition, del f del x is f sub x, and dx dt, well, notice that d dt of x of t, that's d dt of a plus u1t, and that's just u1. So that's where that comes from. And similarly for u2. So we wind up with this very slick formula for the directional derivative. And in fact, we can make that even slicker by realizing that this looks like a dot product. So it's f sub x, f sub y dot u. This whole thing, remember, was just our unit vector in the direction we want to go. And this guy will be important in its own right. We'll call it the gradient, and we'll encounter that in just 15 minutes. So let's do an example. Let's find the directional derivative of f of xy is xy squared in the direction 1, 1 at the point 1, 1. So is this guy u? No. Always remember that u must be a unit vector. So step 1 is always to make the direction a unit vector. So our u, that will be 1, 1 over its magnitude. That's 1, 1 over square root of 1 squared plus 1 squared. And this is our u. And now that we have that, now we can plug this into the formula. So we found that u is root 2 over 2 comma root 2 over 2, making our direction of unit length. And now we plug in. So d sub u of our function evaluated at 1, 1, that is this. Y squared is del x of f, 2xy is del del y of f dot u, and we're evaluating that at the point 1, 1. Plugging in, we have this, and computing that, we have 3 root 2 over 2. And roots of some kind will be common in directional derivatives due to the normalization of the direction, which results in square roots due to it being dividing by a magnitude. So that is the slope in the direction 1, 1 at the point 1, 1 of that function. So I encourage you to pause the video and try your hand at finding this directional derivative. Okay, so step 1, we make the direction a unit vector. Our direction is 3, 4. We divide that by its magnitude to scale it back to be of unit length. And we find that u is 3/5, 4/5. And now that we have that, we can plug it into our formula. So our directional derivative evaluated at the point 1, 0 is, plugging in, this. These are the partial derivatives of this function, dot u, which consists of u1, u2, evaluated at 1, 0. So now we plug in our point 1, 0 into this, and we get this, and evaluating that dot product, we have 2. So the directional derivative of that in that direction at the point is a rise over round of 2. And that's really all there is to directional derivatives. But now we introduce a very important concept that we'll be using throughout the rest of the course. And that is the gradient. So in that directional derivative, remember that we could write this as a dot product of this and that. And this guy here, that's a very important concept in its own right. That is called the gradient. The gradient vector captures the slope in the x and y directions. So it consists of, well, f sub x and f sub y, the partial derivatives in the 2 directions. And we denote it with this symbol. This is the gradient symbol, and we pronounce it as grad f, or gradient of f. This is just a kind of shorthand pronunciation that you might hear me say sometimes, and other professors who use this. So the gradient of f consists of its 2 partial derivatives, and it's a vector. So using this notation, our directional derivative can thus be expressed as the directional derivative of f in the direction u is grad f dot u, since this guy was grad f, and that's u. So let's do an example. So let's find the gradient of xy squared at the point 2, 3. Okay, so first, the gradient of xy squared consists of the 2 partial derivatives. It's del del x of xy squared, comma del del y of xy squared, and that is y squared, comma 2xy. And then the gradient of this function evaluated at 2, 3, that means y squared, comma 2xy, evaluated at the point 2, 3. So we plug in, and the gradient there is 9, 12. Okay, and what does the gradient mean intrinsically? So we've seen that the directional derivative is grad f dot u, and now let's look at the geometric definition of the dot product. So remember that the geometric definition of this would be the magnitude of the first part times the magnitude of the second times the cosine of the angle in between them. But u is of unit length, so it's just 1. The magnitude is just 1, so it goes away. And therefore, the directional derivative is the magnitude of the gradient times cosine of theta. Now, when is this maximized? Well, cosine of theta is maximized when theta is 0, because then cosine is 1, and that's the largest that cosine can be. But if this is the case, then it's maximized in the direction of the gradient. So in other words, this dot product has a maximum when the first part is in the direction of the gradient, because that's when the cosine is maximized. Because I should note, direction in the same direction, that means that the angle between them is 0. So this part, angle being 0, is the same as them being parallel, so it's in the same direction. And what that means is that the gradient vector is the direction of the steepest slope, and its magnitude is the steepest slope. And this is a very important thing for intrinsically what the gradient is and why we care about it. The gradient is in the direction of the steepest slope. So let's do an example just to illustrate what we're talking about here. Suppose that you're climbing out of a valley modeled by this paraboloid, and suppose that you're standing at the point 2, 3. So here's the picture. We have this paraboloid, and you're standing at a point. In which direction should you walk if you want to increase your elevation at the fastest rate? Should you walk this way? No. Walking that way, you'll stay at constant elevation. Should you walk this way? Nope, it doesn't look a bit like the steepest direction. The steepest direction looks like it would be in this direction. And what direction is that exactly? Well, that is the gradient. The gradient is the direction of steepest slope. So for part A, we find the gradient of f, and we get that the gradient at that point is 8, 6. So we want to walk in that direction. This didn't specify the magnitude of the direction, so we could also scale it back. If we wanted a unit vector in the desired direction, it would be this, dividing this by 10, scaling it back. And I should note that the gradient, that doesn't mean the XYZ direction, it means the direction that you would be going in the projection down onto the XY plane. So for part B, to keep our slope 0, we can think of it this way. If you go perpendicular to the direction of steepest descent, imagine a planar linear approximation. If you go perpendicular to the direction of steepest ascent, then you are staying at a level contour curve. So what we want to find for part B is something orthogonal to the gradient vector. So how can we find an orthogonal vector? Well, recall that orthogonal to a vector AB is the vector negative b comma a. That's in general because AB dot negative b comma a is negative AB plus AB is 0. So such a vector is negative 6 comma 8 or 6 comma negative 8 or 3 comma negative 4. These are all in the same direction. All of these are parallel and in the direction of slope 0 because they're all orthogonal to the gradient vector. And I should note that, well, clearly there are more than just these. There are infinitely many parallel vectors, and they're all orthogonal to the gradient vector, all orthogonal to the direction of steepest slope, and that means all of slope 0 if you're going in these directions. So here's a picture of what we just did. These have different numbers, but it's the same idea. We were in this valley and at a particular point, and the direction of steepest descent was the gradient. And let me clarify, the gradient is not this vector in R3, it is this vector in R2. And if you walk in the direction of the gradient on the XY plane, then that means that your Z coordinate above that gradient will increase most quickly. And the direction of steepest descent is the opposite direction of the gradient, it's negative. And orthogonal to the gradient, that is the direction of circumambulation, i.e. a level curve staying at the same elevation. So therefore, important to note, the gradient is always orthogonal to any level curve at that point. So this summarizes what we've learned. F has a maximum rate of increase in the direction of the gradient, and the magnitude of the gradient is that rate of increase. In the opposite direction of the gradient is the rate of steepest decrease, and the directional derivative is 0 in any direction orthogonal to the gradient. And by this, the gradient vector is always orthogonal to the tangent line to a level curve at any point, which is what this says. I won't go through this example in depth, but it's a nice illustration of how the gradient might apply to some things in physics. We'll actually see way more things that will be accessible later in this course. But suppose that a ball is rolling down an incline and it's essentially massless, so it has no inertia really. Then the ball will always go down in the direction of steepest descent, and that means that it is always in the direction of the gradient, and that direction of the gradient is always orthogonal to the level curves. Okay, so let's do another example, this time utilizing what we learned about how the gradient is always orthogonal to the level curves. Let's find the tangent line to the level curve of this function at the point 2, 3. Let's draw a picture to help visualize this. So this is a paraboloid, and its level curves will be ellipses like this when you set this guy equal to a constant. And at the point 2, 3, here is 2, 3, we have a tangent line, and the gradient at any point will always be orthogonal to the level curve at that point, and thus orthogonal to the tangent line. So one way we can find this tangent line is to find the gradient and then find a vector orthogonal to that gradient, and then make a line through the point that is parallel to that vector. Okay, so the gradient of f at the point 2, 3, that is 4x, 2y, the partial derivatives evaluated at 2, 3, and that is 8 6. And orthogonal to this is 6 comma minus 8, as we found. You can verify and remember that for a vector in R2, you just swap them and put a minus sign by 1, and then the dot product is 0. Okay, and this vector here, that will be like that vector. And now the line that we desire, the tangent line, is going to be r of t is 2, 3 plus t times 6 comma minus 8. That would be in vector form. Okay, or we could think about how 6 comma minus 8, that means that the slope m is the rise over run is negative 8 over 6. So we have, well, y minus y naught is m times x minus x naught becomes y minus 3 is negative 4/3 times x minus 2. So that's just two equivalent answers for the same thing in different forms. Now, directional derivatives and gradients also apply in 3 dimensions or higher, and it's exactly what you would expect. The gradient in 3 dimensions is the vector consisting of the x, y, and z partial derivatives, and the same rule about how to find directional derivatives still applies. du of f is grad f dot u, where you use a unit vector in the direction you want to go. And it's also still the case that the gradient vector points in the direction of steepest slope. Its negative is in the direction of steepest descent, and the directional derivative is 0 in any direction orthogonal to the gradient. I don't think it's worth doing a problem here because the math is all exactly the same. It's just that now you have a third component, but everything's identical. So that concludes directional derivatives and gradients. Have a great one.